Okay, sorry for the interruption. My Apple Pencil decided to give up its charge at a really inconvenient time. All right, so where we left off is that we were on the third of our three major rock types at Pelican Rapids, and these are the so-called politic enclaves. So in these two photos, the politic enclaves are the dark bits. Okay, so the politic enclaves, the top photo is that dark colored block there. The politic enclave in that lower photo is that rock there, and I've abbreviated politic enclave as PE. Okay, so the first and most obvious observation is that the politic enclaves are rich in dark colored minerals, hence they're dark colored themselves. Okay, so rich in dark colored minerals. Okay, and I'll talk about what those minerals are in just a moment. The second observation is best seen in that top photo, which gives you something of a three-dimensional view of what these enclaves look like. And what I want you to notice is that these enclaves have a sort of lozenge shape. Okay, so that they're shaped sort of like a watermelon seed, meaning that they're surrounded on all sides by granite. Okay, and in particular, the granite that's surrounding these enclaves is phase 2 granite. And to illustrate that, I'll just go back to the geological map. And what I want you to notice on that map is that the politic enclaves and the samnitic enclaves are spatially associated specifically with phase 2 granite. They're not associated with phase 1 granite. So either phase 2 granite completely surrounds those enclaves or they're immediately adjacent to those enclaves. Okay, so the other observation is that these politic enclaves are surrounded by phase 2 granite. Okay, and the third observation is best seen on the polished surface of that lower photo, is that if you look carefully at that politic enclave, you can see a banding to it. There's a layering, a metamorphic layering to it, defined by that dark blue colored mineral alternating with that sort of orangey colored mineral. Okay, and if I just trace it out, the layering is oriented something like this. Okay, and what I want you to notice, and the important point that I want you to notice, is that that layering extends until you get to the phase 2 granite, which is here. So it looks like that the phase 2 granite truncates or cross-cuts the metamorphic layering in the politic enclave. Okay, so the observation is the metamorphic layering in the politic enclave is cross-cut by phase 2 granite. And if you think back to something you learned in intro geology, is there's the law of cross-cutting relationships. So if you have two rock types and one rock type cross-cuts another, the rock that cross-cuts is the younger of those two rocks. So in this case then, by that law of cross-cutting relationships, phase 2 granite is younger than the politic enclave because it cross-cuts the metamorphic layering in the politic enclave. Okay, so the picture to take away, the picture to have in your mind is basically you can think of these politic enclaves as these blocks, these lozenge-shaped blocks that are essentially suspended in phase 2 granite magma. That's what they are. They're sort of meter-scaled blocks suspended in that phase 2 granite. Okay, so those are the physical observations. What I want to move on to then is to try to make some assessment of what the origin of those politic enclaves were. And I want to talk about two issues. One is, what was the parent rock for those politic enclaves? What were those rocks before metamorphism? And secondly, what kind of metamorphic pressure temperature conditions did it take to produce the mineralogy, to produce the mineral assemblage that you see in the politic enclaves? Okay, so let's first address the parent rock issue. So presently, these are metamorphic rocks, and all metamorphic rocks are changed from some pre-existing rocks. So those pre-existing rocks could have been of sedimentary origin, or they could have been of igneous origin. And we want to try to determine which it was. What was the nature of the parent rock for these politic enclaves? A clue to what the parent rock might have been comes from the composition of the minerals that make up the politic enclave today. Okay, so there's several minerals in that photo that you can make out with the naked eye. The first mineral has a roughly circular shape and it has a blood red color. So there's 3 grains of that mineral. Here, there's a very large grain right there. There's another grain right there. And all of those are grains of the mineral garnet. Okay, so garnet has a blood red color. So this rock, the politic enclave, is rich in garnet. The second mineral that you can make out with the naked eye has a very dark blue to black color. So that's this stuff over there. And that's the mineral cordierite. Okay, and so there's lots of cordierite in this politic enclave. Another mineral that you can make out with the naked eye has, instead of a blood red color, sort of has a pink color, and there's quite a bit of it there. And so here's an example, and that's the mineral potassium feldspar. So the chemical symbol for the element potassium is K, so we refer to that as K feldspar. So potassium feldspar. Those are the minerals that you can make out, those 3, with the naked eye. If you look at this rock under a microscope, there's several other minerals that you can pick out. There's the mineral sillimanite, okay, and there's the mineral spinel. Now, I've given you the chemical formulas for all of those minerals. Don't worry about the details of it. The only point I want to make with the chemical formula is that all of these minerals, and in particular the first 4, all of those minerals are rich in the element aluminum. So all of these are aluminum, or Al, rich minerals. So in assessing a protolith, a parent rock for these politic enclaves, essentially what we want to find is a parent rock that's rich in the element aluminum, because that's the characteristic of the politic enclaves. Okay, and a parent rock, or parent rocks, that are very rich in aluminum, okay, are the sedimentary rock type mudstone and shale, which are basically the same thing. So mudstones and shales are rich in aluminum, and the simple reason for that is the dominant mineralogical constituent of mudstones and shales are clay minerals, okay, and all clay minerals are aluminum rich. Okay, so a likely protolith for these politic enclaves was a mudstone or a shale. They have the right chemical characteristics, that aluminum-rich chemical characteristic, to make them a likely parent rock. Okay, so that's the parent rock of the politic enclaves. I'll just say the following about the 4th and minor rock type in the Pelican Rapids outcrop, which were the Samitic enclaves. And those, as I mentioned, are closely related to the politic enclaves, and the only difference is that instead of being a regular mudstone, a samite is a mudstone that was sandy. So it's a sandy mudstone. So it has a little bit more quartz than a regular mudstone would have. But otherwise, it's quite similar. It has a similar origin. Okay, so that's the issue of parent rock. The next issue we want to address is what kind of pressure temperature conditions did it take in order to produce the minerals, the mineral assemblage that you see in the politic enclaves. And you can do that by taking not only the types of minerals that are present in the enclave, but also the composition of the minerals. And you can take that information and quantitatively calculate the pressure and temperature conditions of metamorphism using the principles of thermodynamics. Okay, and when you do that, The pressures that you get are pressures between about 7 and 8 kilobars, which corresponds to pressures of 7,000 to 8,000 bars of pressure. And to give you some sort of reference, atmospheric pressure is roughly 1 bar. So this is 7,000 to 8,000 bars of pressure. So those pressures correspond to rocks that are buried in the earth to depths of between about 24 and 28 kilometers. So that's the depth at which this metamorphism was going on. The temperature of metamorphism was very high. Calculations indicate that the temperature of metamorphism here was between about 900 and 1,000 degrees Celsius. And those are very high temperatures. By way of comparison, standard metamorphic rocks that you see all over the world metamorphose typically at pressures between about 300 and 700 degrees C. So these temperatures in excess of 900 degrees C are very high. There's actually relatively few places on Earth where these ultra high temperature metamorphic rocks are preserved. Pelican Rapids is one of them. Okay, so at these extreme temperatures, if you take a mud, subject them to these extreme temperatures, what you're going to get is extensive melting of these rocks. The rocks will undergo this process known as partial melting. That is, when you melt rocks, they don't all go molten at a single temperature. Rather, what happens is that part of the rock becomes part of the rock goes molten, while the rest of the rock remains solid. The melt that's produced in that process will have a roughly granitic composition. That is, when that melt crystallizes, it will crystallize to form a granite. And the unmelted stuff, the stuff that remains solid, the solid residue, will have a mineralogical composition that resembles the mineralogy that you see in the Pelitic Enclave. That is, that it will be rich in minerals like garnet and cordierite and spinel. Okay, so what we think is that the Pelitic Enclave is a residue of this high temperature melting process. The observation is that if you look at the mineralogy of phase 2 granite, in addition to quartz and feldspar, which are the major minerals, there's also small amounts of garnet and cordierite and sillimanite and spinel, the same minerals that are in the Pelitic Enclave. The proportions are very different, but the mineralogy, the types of minerals, are actually the same. And on that basis, what my students and I concluded is that phase 2 granite is basically a high temperature partial melt. It's a crystallized melt that was produced by melting these original shales and mudstones. Okay, so at Pelican Rapids, we both have the melt product, the crystallized melt, as well as the source rock that produced that melt, the source rock from which that melt was derived. Okay, so what I want to finish off with is, in the final slide, is want to step back a little bit and place the Precambrian geology that we've been talking about in northeastern Alberta, I want to place that into the broader context of the Precambrian geology of all of Western Canada. So what's shown on this map here are the different Precambrian crustal blocks that we find in Western Canada. And what distinguishes one block from the adjacent block is one of two things. One is that the proportions of rock types in each block might be somewhat different. And even more importantly is the ages of rocks in each block. So those two criteria, the types of rocks and the ages of the rock, distinguish one crustal block from the adjacent crustal block. Okay, and some of these Precambrian rocks shown in this map are exposed at the surface where you can study them directly. But some of these rocks are buried underneath younger sedimentary rocks. Okay, and that's particularly true in the western part of this map area. So what's been done to prepare this map is that those younger sedimentary rocks have been stripped away to reveal the basement blocks, the basement terrains that are buried underneath. Okay, so to get you located on this map, this body of water here, this one, is Lake Athabasca, which we talked about. Okay, and this rectangle here, okay, those are the area where the Precambrian rocks are in northeastern Alberta. And what I want you to notice is that Pelican Rapids and the rest of the Precambrian rocks in northeastern Alberta are part of this much larger belt known as the Tulsen-Thelon Belt, which extends from here in central Alberta, where it's buried underneath younger sedimentary rocks, and extends northward for about 3,000 kilometers all the way up into the Arctic islands. Okay, and what characterizes the Tulsen belt is that it's dominated by igneous rocks with some metamorphic rocks, and importantly, the age of magmatic activity and the age of metamorphism in the Tulsen-Thelon belt is primarily between about 1.9 and 2.0 billion years ago. Okay, so what we want to do is try to assess, try to determine what tectonic setting the Tulsen-Thelon belt formed in. In order to do that, what we typically do is look for modern day analogs. So where on the modern day Earth do we see simultaneously deformation, magmatic activity, and metamorphism going on in a very laterally extensive belt, a belt that's thousands of kilometers long? One place where that's happening today is in the Himalayas. Okay, so we have this long belt where simultaneously you have deformation, magmatic activity, and metamorphism going on. Okay, so the Tulsen-Thelon, like the Himalayas, is this very extensive belt. And the way the modern day Himalayas is forming is through the collision of two continental blocks. So in the case of the Himalayas, they're forming in response to the collision of the Indian subcontinent with the Asian continent. And that collision has produced the Himalayas. Okay, and you get this deformation, this belt-like zone where you have all these processes going on directly at the collision site. And you also get belts of deformation and metamorphism happening inboard of the collision. About 1,000 kilometers north of the Himalayas in Central Asia is a belt that runs parallel to the Himalayas, known as the Tian Shan belt, okay, which is also due to the Indian-Asian collision. Stresses of that collision have been transmitted inboard. So whether the deformation happens right at the actual collision site or inboard of that collision site, ultimately, these belts are the product of continent-continent collision. So that's what we think was responsible for the Tulsen-Thelon belt. It is a collisional belt formed by the collision of different continental blocks. Okay, the difference between the Tulsen-Thelon belt and the modern day Himalayas is that the modern day Himalayas, the thickness of continental crust there is roughly double the normal thickness of continental crust. So normal continental crust is about 40 kilometers thick. In the Himalayas, it's about 80 kilometers or more thick. And it's that large crustal thickness that gives rise to the height of the Himalayas. Okay, large crustal thicknesses causes the mountains to rise. However, as the Himalayan mountains have gone up, erosion is happening on the top and they're being eroded down. And if we wait some time, if we wait 50 million years, if we wait 100 million years, all of that stuff off the top will be eroded and the Himalayas will go back to normal crustal thickness. Given that the Tulsen-Thelon belt is a very ancient belt, it formed more than 1.9 billion years ago, those erosional processes have had time to take place, and what we're seeing in the Tulsen-Thelon is a deeply eroded version of either the Himalayas or that inboard mountain belt called the Tian Shan. Okay, so the picture to take away from the lecture is what the rocks in northeastern Alberta were and the larger belt which those rocks are a part of, the Tulsen-Thelon belt. So if you were here in Western Canada 1.9 billion years ago, what you might have seen is a mountain belt, Himalayas, or that Tian Shan.